All right, hello and welcome to the intro video on section 5.1, which is on sequences. I apologize for the ridiculous lighting of the room that I'm in. I look like an Inspector Gadget villain, but it doesn't matter anyway, because as always, we're going to cut over to the iPad real quick. This is going to be a short video because frankly, this section isn't really that interesting in and of itself to us. It is interesting just because it's a means to an end, a very important end. And on that note, there's a fantastic video that your instructor can share with you. It might already be on your latte page, prepared by one of the other instructors, of like an overview of chapters 5 and 6. It's a really, really nice sort of big picture, because it is very easy for students in these two chapters to sort of lose the forest for the trees, if that's an expression you're familiar with, meaning it's easy to get so caught up in like the technical details and the minutia that you forget what it is that we're doing this for. And to be quite honest, your book doesn't really do a good job of telling you. So again, ask your instructor for the video on like a Taylor series overview, it's called. It's long, but it's definitely worth a watch. All right. But what is section 5.1 about? Well, it's called sequences. And all we're going to do in this video is basically talk very briefly about what a sequence is, the way in which sequences arise, the kind of examples that we're going to deal with, and then one or two theorems about them, and then I'll turn you over to the reading, and I'll see you on the other side for a simple worked example video. So a sequence in mathematics is extraordinarily general. It is literally just an ordered list of real numbers. So, sorry, there's a brief interruption there, although you may not have realized it. A sequence is literally just an ordered list of real numbers. And we will generally, but not always, assume that that ordered list is indeed infinite. But this doesn't actually need to be part of the definition. If you want to be pedantic, you can call this an infinite sequence. And I think that's actually what your book does, which is fine. So an infinite sequence is an ordered list of real numbers, and we typically write this list as a sub 1, a sub 2, a sub 3, ... Now you have this term, which usually in this setting, people will tend to denote as a sub n, although sometimes people use a sub I. It doesn't matter. It's literally just a dummy variable that's there to indicate what a generic term of the sequence looks like. And then, of course, in the infinite case, that list would go on. A very nice and concise shorthand for this is to write it like this. So what this terminology is saying is the elements of the sequence are a sub n's, where n starts from 1, goes off to infinity, and again, that's because it's an infinite sequence. The common types of sequences that we will encounter can either be, so they'll have some names. So they're either explicit, and this is typically where the nth term of the sequence is actually given by finding some explicit formula f and plugging in the number n. So an example of this, for instance, let's suppose that we had the following sequence. So it started with -1/2. By the way, turning the ordered list into an explicit sequence, it's not always easy. So I'm going to do this quickly, but you may find this challenging at first. You're going to get lots of practice in the reading and the homework. 1/4, -1/8, 1/16, -1/32. Continuing on, and the question, oh, hold on one second. Seems to have stopped sharing for some reason. Let me try and fix that. Here we go, sorry. So now you can see the terms that I was writing. So we have a sequence here given by -1/2, 1/4, -1/8, 1/16, -1/32. Goes on, and we want to understand, is this an explicit sequence? And indeed, in this case, it is. The top, so basically remember, I want some formula where if I plug in, say 1, I get this term. If I plug in 2, I get this term. If I plug in 3, I get this term. 4, I get this term, etc. So what does that look like? Well, I notice the top is oscillating back and forth between -1, and it starts on a negative. So this looks like -1 to the n. And the bottom is getting multiplied by 2 each time. So this is going like 2 to the n. And this is indeed what A sub n looks like. And this is an example of an explicitly given sequence, because I'm just being told directly what the nth term of the sequence is. And the point is that unlike the other example that we're about to touch on briefly, don't need to know the terms that precede it in order to understand what the nth term is. So the alternative to this, that we won't necessarily see, but which shows up a lot and which people talk about, is a so-called recurrent sequence. A recurrent sequence tells you how to get the next term from the previous. And sometimes it's just from the immediately preceding term. So for instance, I might tell you that a1 is negative a half, and that the an plus 1, the n plus first term of the sequence, is negative 1/2 times an. So here, what's going on is I'm telling you where you started, and I'm telling you if you know an, how can you obtain an plus 1? And in this case, it's namely multiplying it by negative 1/2. As it happens, this is another way to describe the same sequence. You should actually convince yourself of that. If you follow this pattern with this starting point, I claim you'll get exactly this set of numbers. Another very famous example, which doesn't have quite such a nice property in terms of writing it out in a closed form, are the Fibonacci sequence, which I'm going to hope I just spelled correctly. Says that fn plus 2 is fn plus 1 plus fn. So in other words, each term is the sum of the preceding two. As usual, I need to tell you where to start. So we're going to take f of 0 to be 0 and f of 1 to be 1. So let's write down a couple terms in this sequence just to understand. So we start with 0 and 1. Now the second term, which would go here, is by definition the sum of the ones before it. So it's going to be 0 plus 1, which is 1. The third term, which will go here, is by definition the sum of the ones before it. So it's 1 plus 1, or 2. The next term is the sum of the two before it, so 2 plus 1, which is 3, 5, 8, 13, 21, etc. And it just keeps going and going. This sequence, by the way, is very fascinating. Shows up a lot of places in nature and in art. It has some connections with psychology, although from a mathematics standpoint, I'm kind of like, I don't really know what that means. But it is quite beautiful. It creates some absolutely beautiful pictures. And supposedly it's tied to some sort of innate recognition of beauty, according to some psychological experiments that they've done in terms of proportions. And it leads to something called the golden ratio. There's a student project in the book after the reading, before the exercises. It's totally voluntary, but if you're interested, it has to do with the Fibonacci numbers, and you work out something about their limiting properties. Okay. So we won't deal as much with recurrent sequences in this class, but the one nice thing that we need to understand about the explicit sequences, so I'm looking right here, is how the terms behave as n goes off to infinity. I mean, limits are something that we deal with a lot in this class. So you can ask, what does this expression mean? What does it mean to take the limit as n goes to infinity as a sub n? And again, the answer shouldn't surprise you. We'll say that that limit is equal to some L if, as n gets large, a sub n gets close and stays close to L. Similar definition to what we had when we talked about the convergence of a function to a value, although technically we never talked about that. It's part of the prerequisites for Math 10A. We have a great theorem, however, that's going to tell us how to do this. So the theorem says, if you have a sequence which is defined explicitly, and the limit as x goes to infinity of the function that you've used exists, this won't always be applicable, but it will very often be applicable, then the limit as n goes to infinity of a sub n is the same. And there's a very nice picture in your book of what's going on. You just have these dots basically representing the sequence values at integer values on the graph. So if you thought about graphing f of x, well, if you pick every point on the graph out at the integer values, those values would be the sequence values of a sub n. So if the graph is getting and staying close to some point, the a sub n's get taken along for the ride, and there's really nothing that they can do. Other theorems from the section, There are a lot of them, but realistically, we're not going to pay that much attention to them. There is an absolutely beautiful theorem, and if you take analysis, which is Math 110A, which you would do, for instance, if you were an applied math major or a pure math major, the theorem that bounded monotone sequences converge is hugely important, hugely important in mathematics. But in this class, for our uses of sequences, we're not going to have that much use to put to it. So I suggest you read it, but I don't think we're going to ask you a question that would rely on it, although I'll check with the other instructors to make sure. If we decide to change our mind about that, we'll communicate it. Again, the sequences themselves, it's a pretty broad definition. So just understanding their behavior, being able to convert back and forth from, given an explicit formula to write out the first few terms, given the first few terms to write out an explicit formula. Those are important traits, again, because of how sequences are going to function for us going forward. And then I guess I want to mention two other types of particularly important sequences, and then this will close the video. So these are recursive sequences, although they can be made explicit. So actually, let's do that. So let's start with them as a recursive. We'll turn them into an explicit formula. So there is an arithmetic sequence. And an arithmetic sequence looks like the following. Basically, it says that a sub n plus 1 is always equal to a sub n plus some fixed constant. And then, of course, as usual, I have to tell you where the whole thing starts. So anytime you have a recursive formula, you're being told how to get new terms from the terms you have, but you have to be given some seed. You have to be given something to start with. So here, what this is saying is I start somewhere, and then each subsequent term just adds c to it. So let's write out the first couple of terms, and let's turn this into an explicit formula. Again, this is just good practice. So the very first term of the sequence is a, because we're told that. The next term, of course, would be obtained by taking n equal to 1 in this expression. So it's a1 plus c, and in this case, that would look like a plus c, because of course a1 is nothing but a. The third term of the sequence is taken by taking n equal to 2 here and here. So we want to take a2, and we want to add c to it. So we get that a3 is a plus 2c, a plus 3c, and the pattern would continue. And so in particular, if you wanted a closed form for this, well, f of n is a plus n minus 1c. So again, these types of sequences, they'll show up a little bit, but more than anything else, arithmetic sequences are a term that show up a fair amount just in life. I know I say that and you're probably thinking, I've never encountered them, but maybe you will now that you know what they are. You just didn't know what you were looking for. The second type of sequence that can show up sometimes is called a geometric, and it is defined similarly. So for a geometric sequence, each new term is obtained from the previous by multiplying by some fixed r. We tend to use the letter r because it is the ratio of the terms. Notice that this is the same as saying that r is an plus 1 divided by an. So each new term is obtained from the previous by multiplying by the same number. Therefore, the ratio of any two adjacent terms is the same. And as usual, you have to kick this off with a1 equals a. So let's try this. So the first term of our sequence is a. The next term is obtained by multiplying by r. So we get ra, r squared a, r cubed a, r to the fourth a, etc. We're going to deal with this kind of situation a lot in the next section, but where we deal with this as a series, not as a sequence. But nonetheless, it's good practice to get used to these terms, understanding their behavior. In particular, whether or not they approach a limit is a great question. And if we were to write down an explicit formula here, well, what you notice is that the nth term is obtained by starting with a and then multiplying by the common ratio n minus 1 times. So by the way, it can be a little tricky to make this guess when you're starting out with this. So what I would do, just like when you take an antiderivative that's tricky, you can always check by taking the derivative. I would write down your formula, and then I would just write down the first couple terms. If you're getting the same terms, then you've done it correctly. So if you're not sure whether this is correct, just try it. So if n equals 1, this term would be 0, so r would vanish, and we would just get a, check. For n equals 2, we'd get 2 minus 1, so that's ra, check. n equals 3, r squared a, and by now I'm pretty confident that this in fact is the correct formula. It's going to line up with all of this. So again, it's like anything. It is easier in general to write down the terms of the sequence from the explicit form than it is to write down the explicit form from the terms of the sequence. But that's the same as it's easier to check that something is a solution to a differential equation than it is to solve it. That it's easier to take a derivative than it is to take an antiderivative. But all of these processes are in some sense inverse to one another. So if you solve a differential equation, you can always check by just checking that your solution is indeed a solution. That's an easy check to a hard problem. Or if you take a hard antiderivative, you can always check that you did it correctly by taking the derivative. You'll undo all the work you just did, and you should get back where you started. Here, if you think you've written down this expression correctly, just write down the first couple terms of the sequence, and if you're getting this, then you've done it correctly. All right. So again, there's some more stuff in the section, but by and large, it's not going to be terribly important for us. So I would even say you probably don't need to read the stuff about bounded and monotone sequences. The squeeze theorem is a good theorem to have in your back pocket, and we may make use of it. And just understanding, again, the main takeaway from this is what is a sequence, and what are some types of sequences, and how do I take a sequence and write down an explicit formula, take an explicit formula, write down a sequence. How do I find the limit of some sequences? And in that regards, this theorem here and the squeeze theorem are the two biggies in the section. All right, I will see you in a minute with a worked example video highlighting some of these strategies. So go read the chapter and leave some comments on perusal.